All right, we're going to start today by reviewing everything that we've learned so far, which are the geometric series and the telescoping series. And for these two, when we actually find that they converge, we can find the sum. So the geometric series converges if the absolute value of r is less than 1, and the sum of the infinite series is the first term divided by 1 minus r. For telescoping, we rarely will see these, and the AP exam will not test them, but when you end up taking the limit of your decomposed fraction after you've collapsed all the terms that cancel out, whatever limit you get is the sum of the telescoping series. For all other series, when you get a number out of your convergence test, the number is quite meaningless, not quote meaningless, and does not give us the sum of the series. We also learned the nth term test for divergence. This only determines whether or not a series diverges. It tells us nothing about convergence. So all we can say is that if the limit of the underlying sequence as n approaches infinity is not equal to 0, then the series diverges. And here's an example. This one has a degree of 3 in the numerator, and when I multiply out this one, I end up with a degree of 3 in the denominator. So my limit as n goes to infinity is going to be the ratio of the leading coefficients of 4 over 1. So if I can write this expression out, 2 plus 4n cubed over, and if I multiply out the n, I get n cubed plus 4n. I want to look at the ratio of the leading coefficients here, 4 over 1. This limit is 4, which is not equal to 0, and therefore this series diverges. All right, the integral test. This is our not so favorite test because it takes a long time. What we need to do is rewrite the expression in our series as an integral, and then we are going to integrate from 1 to infinity. And of course, we're doing an improper integral, so we really want to replace that upper limit of infinity with t and take the limit as t goes to infinity. So this one looks to need u substitution because the natural log of n differentiates to 1 over n. So let's do a u sub with the u equals the ln of n and the du as 1 over n dn. Now I can rewrite, I have the limit as t approaches infinity of the integral, and I'm not going to put in limits of integration right now because I'm going to write this in terms of u. I basically have u du, and when I integrate u du, it goes to u squared over 2. And so now I'm going to sub back in and rewrite this integral in terms of n. So I have the limit as t goes to infinity, and I had u squared over 2, which is really just the ln of n squared over 2, and I'm evaluating that from 1 to t. Now when I plug in t, I end up getting, well, I need the limit as t goes to infinity again of the ln of t all squared over 2 minus the ln of 1 all squared over 2. And of course the ln of 1 is 0, so this whole term goes to 0. And for this term, as t goes to infinity, the natural log of infinity is infinity, so this limit is infinity, and this series is going to diverge because its improper integral diverges. Next, we talked about the ordinary comparison test, also called the direct comparison test. So in this one, if you think a series diverges, you want to compare it to a divergent series. If you think a series converges, you want to compare it to a convergent series. If the series diverges, you want to compare to a divergent series. Now let's look at these. With a rational function, you're going to look at the leading degrees. So n to the 1 over n cubed. We're going to compare this to 1 over n squared. Now, this only will work, 1 over n squared, first of all, we have to document, is a p series with p equal to 2, which is greater than 1, so 1 over n squared converges. And now we need to show that n minus 1 over n cubed plus 3 is less than the known convergent series to conclude that our series converges. We know that this series is less than because we've subtracted 1 from the numerator and we've added 3 to the denominator. So the numerator is smaller, the denominator is larger, and therefore our series also converges because it is smaller than a known convergent. Just remember, when you document these, you must document the comparison series and why you know it diverges or converges. For this next one, looks like we have n squared over n cubed, so we're going to compare to 1 over n, which is a p series, and actually you just have to say this is the harmonic p series, and it is known to diverge. It's harmonic because p equals 1, and you can state that, but it's enough to just say it's the harmonic p series and therefore diverges. So you want to show then that your series, 6n squared plus 1 over 2n cubed minus 1, is larger than a known divergent. And if it is larger than a known divergent, it will also diverge. Well, this one's larger. First of all, 6 over 2, the ratio of the leading coefficients, is 3, which is larger than 1. Plus, we're adding 1 to our numerator to make it bigger, subtracting 1 from the denominator to make the denominator smaller. So this series diverges because it is larger than a known divergent. All right, one more series to review, one more test to review, which is the limit comparison test. So a limit comparison test does this. A series converges or diverges if the ratio of a given series and some comparison series has a limit. So basically both series have to have positive terms, and what you do is you find the limit of one series compared to the other, and if that limit is some number between 0 and infinity, then both series are going to behave the same way. Okay, so I would look at the ratio of those leading terms. I have n to the 1/2 over n squared. So my comparison series is going to be 1 over n to the 3/2, which, by the way, is a p series with p equals 3/2, which is greater than 1. So our comparison series converges. So now, in order for our series to converge, we have to take the limit. And we are going to take the limit of our series compared to a known convergent series. So we'll have rad n plus 2 all divided by n squared plus n plus 1. And we're going to divide by 1 over n to the 3/2, which is the same thing as multiplying by its reciprocal. And when I do that, and I just look at my leading degrees here, I end up with n squared on the top with a coefficient of 1, and n squared on the bottom with a coefficient of 1. So our limit is 1, and since 1 is between 0 and infinity, both series behave the same way, and in this case that means that both series converge. Make sure that you've explained why your comparison series converges, or you won't get full credit for this.